We're going to do a quick video here on voltage taps. So let's have a look at that. Earlier, if you look at one of the previous videos there, we talk about volts per turn, and we use this transformer to talk about volts per turn, how it works, right? So if you recall, when we apply voltage to the primary, right here, and in this case, rated voltage is 120 volts. We'll get the full 120 volt across all 600 turns. So we establish how many volts per turn based off the primary voltage that we apply and the number of turns on the primary. Now, that is established here and on the primary. Now, whatever is established on the primary is going to be the same as it is on the secondary. So if we establish that it's 0.2 volts for every one turn on the primary, we get 0.2, so one turn, we get 0.2 volts. That's what's going to happen on the secondary. We're going to get 0.2 volts for every one turn on the secondary. So that's how this multi-tap secondary this transformer works. And so this type of transformer is typically used for control voltages or doorbells and stuff like that, where we may have a variety of different voltages. We can buy this transformer, we're pretty much covered. We can go do a 16 volt doorbell or a 24 volt thermostat, something like that in that nature. So that's where these transformers come in pretty handy. Now when we're talking about distribution transformers, that's a little bit different. So when we look at a transformer for distribution, we can also have tap transformers there. And we have it here because we are trying to get the correct secondary voltage. So let's say that my building here, I've got in this case, I've got a 4160 down to 240 volt transformer. So the loads I connect in my building are all rated at, so 240 volts. I do a light bulb, maybe I got a 240 volt motor or something like that, right? And they run best at 240 volts. Well, what happens if I don't get rated voltage on the primary? All right. So let's say that consistently in my building, I only get 3,952 volts coming in. And where I've got my 4160 terminated, okay, is on H1 and the 0% tap. That means that this transformer is expecting rated voltage of 4160, but it's not getting it. So if I put 3,952 volts on the primary, or that's all that's coming in, will I get rated voltage on the secondary? No, right? Let's just have a look. What's the ratio here of this transformer under normal operations? So that is number of turns primary to number of turns secondary. That's how it's established, that ratio. And we know that's going to be the same as the voltage ratio. So under normal operating conditions at 0% tap with 4160 rated primary voltage, I'm going to go down to 240. So we can establish that ratio of this transformer. Let me just grab my calculator here. So 4160 divided by 240 is 17.33 to 1. So 17.33 to 1. So if I only put 3,952 volts on this transformer, so I'll take 3,952 and I will divide it by 17.3333. I'm only going to get 228 volts out on the secondary, so 228 volts. Now that's not really going to be very good for my loads. If I'm only getting 228 volts, these loads are not going to work accordingly. Okay, so they'll be the light bulbs might be a bit dimmer. The motor's probably going to draw a bit more current. A lot of things that probably aren't good for the loads that they may not last as long as they normally should. So this is a very common problem. So what they have is multi-tap transformers on the primary, and this is to compensate for variances in the primary voltage. So let's take the concepts that we have already learned with the taps on a transformer. So, volts per turn. So if I have the full 4160 up here and it's on the 0% tap, I'm going to establish the correct volts per turn that I need for the secondary. Now if the voltage is low, like it was before, 3,952 volts, okay, and I still have the same number of turns, then my volts per turn is going to go down, and it will also go down on the secondary. So I will no longer get my 240. I'll get that 228 or whatever it was. So what can we do? Well, we can de-energize the transformer, and we can terminate it on a lower percent tap. What does that really mean? That means that I'm taking some winding out of the primary so that I can reestablish my voltage per turn where it should be, and then when I get it to where it should be, I'll have the correct volts per turn on the secondary, which will give us our 240 volts for our load. What happens if I'm over voltage? Let's say that I consistently have a higher than normal voltage, say 4,264. So this is out of your ILM, and we're going to go through this little chart. It's on, I believe, page 34, but if it's consistently higher. Well, if I left it on the 0% tap, my volts per turn would be too much if I left it on the 0% tap. So I need to add more turns to get that ratio where it should be. So I have to add turns if my primary voltage is too high. If I don't add those turns, I will go higher than 240. So it'll be out of range, right? So it'll be too high, which isn't good for your equipment either. So that's where this all comes from. We really got to think about the volts per turn ratio. When you see, oh, I'm on a negative tap, that means my voltage is low. I have to take turns out. If my voltage is too high, I have to add turns into the transformer or add more winding into the transformer on the primary in order to get that correct volts per turn. Now, as you see here, I put the formula up here. It says percent tap. It's the actual primary voltage minus the rated primary voltage over the rated primary voltage. So that's the formula that's in your ILM. It works great. I am going to just bring up that chart right here. And let's just use this formula to see how this would work. So here's the, we have a 100 kVA transformer. Its rated voltage is 4160 on the primary or the H windings, and then its rated X windings is 240. So if we're using this as a step down transformer, and we have a low voltage on the secondary or the primary or a high voltage, what do? Well, we can adjust the taps. What tap do we set it on? All right, so here's the little formula here. So they give us some values, and this forms actual primary voltage minus rated primary voltage divided by rated primary voltage. So let's just figure out here. So let's say that I measure 3,952 volts. So actual primary voltage is 3,952 volts. I subtract the rated primary voltage, which is 4160. And then I divide it by the rated primary voltage of 4160. Okay. And then you can times that by 100. All right, so let's see what that would look like. I'm going to grab my calculator here, clear it. So I'm going to move this over a bit for us. So here we've got 3,952 minus 4160 equals. Notice we have a negative number there. That's why we're going to get a negative tap. So divide that by 4160, and we're at minus 0.05, so times 100, we're at negative 5%. So that's your negative 5% tap. We'd have to use de-energize our transformer, set line 1 onto H1, and line 2 would go on the negative 5% tap. Let's try one of the positive values here. Let's say I had the 4,264 volts on the primary. So apply the same formula. What percent tap do we need? Okay, well, it says actual voltage, so that would be 4,264 volts. I'm going to subtract off our rated voltage, 4160 volts, and I'm going to divide that by 4160. and times it by 100. Okay, let me just grab the calculator again. So clear. So we're going to go 4264 subtract 4160. Notice we have a positive value there, and I'm going to divide that by 4160 and equals times 100 because it's a percentage. So 2.5%, and it's plus. So positive 2.5, whereas that one was negative. So we have to add some winding in on the primary. We got to get that correct volts per turn ratio established. Can this be done with secondary voltages? Sure, absolutely. So my actual rated secondary voltage is supposed to be 240, and let's say that I only was getting, let's say 230 volts roughly. So I'm just kind of throwing a number out there. And if I did this, this is actually field what would happen, right? So let's go erase all ink on the slide. Let's say that the secondary, pen, percent tap, let's just use it with the secondary voltages. Let's say that the actual rating or the actual secondary voltage was, I don't know, what did we say, 228 before? So 228 volts, right? And I'm going to subtract 240, divide by 240, and times it by 100. Okay, what would that look like? Let's go grab that calculator. So clear. 228 minus 240 equals minus 12. Divide by 240. 5% tap negative, so times 100. So we can do it with the secondary voltages too. That means that I have to go to the primary and adjust it to the minus 5% tap if I only had 228 volts on the secondary. Anyways, so that's kind of how that works. Sometimes people look at this and go, oh, shouldn't we add turns in? Like plus, we need to add voltage because of the plus. It's exactly opposite. It is if we're low on voltage, we have to set it to a negative percent tap. If we're high on voltage, we have to add it to a positive percent tap. So just a little more on this, transformers. So when you do see these transformers, they're going to be marked out for you. And on the nameplate, you're going to have, obviously it's VA and KVA. So that'd be its maximum load for the transformer. We're also going to have its voltages, its voltage rating. So when there's a low primary voltage, the KVA of the rating of the transformer can be also reduced. So volts times amperage. So if I reduce the voltage and still multiply it by the same rated current of that transformer, the KVA of that transformer can be reduced. So not always. You have to really pay attention to the taps and the tap labeling. So you'll see some acronyms here, like this one says FCBN, and this side says FCAN. So what does that mean? So a transformer that has its KVA capacity reduced to the reduction in voltage would be a reduced capacity tap transformer. When a transformer's KVA rating is not changed with a higher or lower voltage, the transformer is known as a full capacity tap. So it's actually built larger than what's stamped on its nameplate rating in order to take away winding and maintain that same KVA rating. So some of the stuff you'll see is FCBN. What does that stand for? It's a full capacity below normal tap. Okay, so that means I could have a low voltage, drop it down to that minus 2.5 or minus 5%, and everything's fine. I can still load it up to whatever the KVA stamp nameplate is. Okay, so that means it's engineered a little bit better or a little bigger. FCAN, full capacity above normal, same thing. That I can go to a higher voltage tap and I'm fine. I can still load it up to whatever the KVA rating is. And then we have RCBN, reduced capacity below normal, and that's where we would have to watch how much we load that transformer up to. So whatever the stamp nameplate is, I would have to subtract off the 2.5% or the 5% of that. So multiply that 2.5% by the KVA rating and then subtract that from the actual KVA rating, and that'd be the new maximum load I could put on that transformer, or its maximum rating, I should say. Okay, so a little bit on that. Now, tap changing. This can be quite a hazardous situation. Tap taps can be changed on a transformer in several ways. One is the manual reconnection of them. So you physically go there, you undo the terminal, and you put your wire on a different terminal. So manually reconnecting and re-terminate it. Obviously, the hazards with this, we have to ensure that the primary is completely disconnected before we go changing taps. So you have to be wary of this. Are these transformers in parallel? What's the situation? If they are in parallel, I have to disconnect all of them to avoid any backfeeding before I go and lift that wire off. So very important, make sure you are completely de-energized in any way, shape, or form before you try or attempt to do this. Most of the time, like if you're doing a commercial, you're going to have usually it's 600 volt coming in, then you'll feed 600 volt feeders out, and it'll drop down to 122.08. you can usually isolate that pretty good. They don't usually put transformers in parallel, but when you get into any larger distribution, you might see transformers in parallel. So moving connecting bars, that's another way to do it. Sometimes there's a bar you got to move. The use of a rotary switch, that's another item too out there where it's terminated, and you can turn a rotary switch manually, and it'll change the taps for you. And caution, ensure the transformer is de-energized before changing taps. Automatic tap changers also exist. So they sense the secondary voltage with a feedback or control loop, and automatically it's motorized. They adjust the tap to any correct preset value. So that's about it on taps on a transformer.